Today's lecture is going to be on phase noise. Before we start this topic, it's going to be our last lecture on oscillators. Then next lecture, we're looking at power amplifiers. Just a quick announcement. I apologize. I have to cancel tomorrow's office hours. I have to be in San Francisco all day tomorrow. But since I've been unavailable for office hours a couple of times now, I invite you guys, if you have a reason to meet with me, please send me an email and we'll make an appointment. So if you need to talk to me, feel free to send me email and we'll do an appointment. Thursday office hour will be on as usual, and I'll hold it a little bit longer before and after so I can accommodate everybody. Okay? Any questions or comments before we start today's lecture? Yes, Thibault.
The project is due on the 9th of December. Could we have that weekend so that...
I actually wanted to make the projects due as late as possible, so I could make it due as late as the final exam, but I have to also grade everything, so I have to give enough time. So let me review my schedule and I'll try to come up with an optimum deadline. Okay. All right. Any other questions or comments? Okay, so let's talk about phase noise. All right, so phase noise refers to the fact that if you look at the absolute phase of an oscillator, it does not increase linearly as you would expect. So an ideal oscillator, V of t, would have a constant amplitude and basically, let's say, some unknown phase, but this is just a constant, and some fixed frequency, right? So if I look at the power spectrum of such an oscillator, it would be a delta function at frequency omega naught and minus omega naught. Okay? So this is an ideal oscillator. Now, any real oscillator, the spectrum actually does have a little bit of amplitude noise, okay? And it has actually phase noise. So this is some noise signal, noise phase signal, which causes, actually, one way to think about it is the zero crossings of this cosine become a random function. You never know exactly when you're going to cross zero, okay? And if you were to actually plot the power spectral density of a real system, what you would find is that instead of getting a perfect delta function, you have basically a finite width function that looks something like this. And basically, it has a skirt, if you like, slightly outdated terminology. If you zoom in, so it turns out that this is extremely narrow for all practical purposes. It's actually, I'm exaggerating how fat it is. To really look and see how quickly the signal drops, you'd have to zoom into the carrier. So if you actually zoomed in, so let's zoom in to frequency offsets away from the carrier. So this is offset frequency, delta F. And this is a log-log plot. So what you find is that, let's just arbitrarily call this 100 kilohertz. Let's call this a megahertz. Let's say this is 10 kilohertz. Let's say this is a kilohertz, and so on. So what I'm plotting here, this is the log of the power in the signal versus offset frequency. And what you find is this is actually a plot of the relative. So this is the power normalized to P naught, or the power at the center frequency. So if I look here, for instance, at 100 kilohertz, you might find that the signal is dropped by 100 dBc. So quite a bit. So just a small offset away from that peak, and you find that it drops very quickly. And this goes about 20 dB per decade. Okay, so this is just an experimental observation. You also find, so this is called the 1 over f squared region. You find if you go to very high offsets, it actually tends to flatten out. This might be like minus 130 or 140 dBc or something like that, where it flattens out. And if you go really close in, what you find is the slope actually increases to 1 over f cubed, or something close to that. Okay? And so this is an experimental observation. And what you should take away from this is that there is this large 1 over f squared region. So first of all, we'd like to understand where this 1 over f squared region comes from. We'd also like to understand why this is so narrowband, right? Why is it that only a few tens of kilohertz away, let's say omega naught is 1 gigahertz in this example, why moving away from a carrier at a gigahertz so just a little bit, tens of kilohertz, and the power is dropped so dramatically. We'd also like to understand why close to the carrier it goes like 1 over f cubed, and also we'd like to understand what happens at the carrier, because we know there's a finite amount of power in the signal, so this is not going to go to infinity. It's going to flatten out somewhere. Okay? Any questions about this plot here? Just some terminology. We specify phase noise in units of dBc per hertz. So it's how many dBs are you down relative to the carrier at a specific offset. Okay? David?
Those distribution of noise all come from phase noise, or they might also be empty noise somewhere?
At this point, we don't know. So at this point, we're just saying if you look at the spectrum of an oscillator, this is kind of what we observe. And what we'll find out is that close into the carrier, it's almost all phase noise. And when you go out away from the carrier, this tends to be dominated by just a thermal noise in the system. Okay? Yes, Caleb.
So we have the ideal cosine or ideal carrier is basically 2 impulses, right?
That's right.
But once we have phase noise, what's the amplitude and what's the area under the little bump?
Okay, that's a good question. We'll answer that question in this lecture, but to give you a sneak preview, this is actually a Lorentzian function. And the power in this Lorentzian is equal to the power of our oscillator. Okay? Now, the way you can prove that this is a Lorentzian is one way. What's that? We'll talk about it later. But the way you get to that conclusion is that assume that this phase is a white, kind of a Wiener process. It's just the phase is completely random. And then evaluate what the power spectrum of this is. So this is kind of like a 126 style calculation, and then you'll get a Lorentzian spectrum. Okay. So why is phase noise? Why do we care? Okay. So why care about phase noise? Well, there's two important reasons. Actually, there's several reasons. First of all, for the transmitter, it leaks power into adjacent channels. Okay? So if I have a power amplifier connected to an antenna, even if I put a filter here, we're talking about noise very close to the carrier. So let's say that this is transmitting at a gigahertz, and let's say your channel spacing is 200 kilohertz. Okay? That's actually how GSM is. So that means that if I'm at 1 gigahertz, then plus 200 kilohertz is another channel. And so the phase noise of my oscillator, so here's my oscillator, it generates phase noise, and that phase noise basically will leak into my adjacent channel here and perhaps corrupt, if this is a receive channel, because these channels are used as transmitter receiver, then if someone's using this channel as a receive band, their information is going to get corrupted by your transmitter signal. Okay, so that's very simple. Another reason we don't like it is a little more complicated. It's due to, on the receiver side, it's due to reciprocal mixing. Okay, And the idea is as follows. So let's say that I have an LO and I have my RF signal here. And let's say there's a big interfering signal here. Let's call this the jammer. Now, and let's say there's actually another jammer here. Now normally I would really worry about this second jammer, right? Because this second jammer is the same IF distance away, and so this can do, in a normal mixer, even if I have an ideal LO, this second jammer will really mess things up, right? We have to worry about it. So we have to have an image reject kind of mixer topology or some kind of image reject filtering. Now another problem with jammers is, let me draw another picture. Let's say that there's no jammer signal present, but we have phase noise. Let me draw it like this, actually. So let's say that this is my LO signal, this is my RF, and this is a jammer. And the jammer is, let's say, 2 channels away. So it's not in the image band, it's actually just 2 channels away. Now, if you remember what multiplication is basically convolution, right, in the frequency domain. So if this is not a tone, then really what happens is when I multiply this signal by the input, which consists of these 2 tones, I get convolution. And because of these skirts, I'm going to leak power into my desired IF band due to this jammer. Actually, a very simple way of looking at it is that this jammer tone has an LO, which is actually the skirt of my real LO. So because I have phase noise, I actually have a continuum of LOs to use to take jammers down to the same IF. So the phase noise acts like an LO for jammers. Okay? And hopefully that the phase noise is very small, so the mixing action you get is very small. But nevertheless, it's there. So if your jamming signal is 100 dB bigger than the signal you're trying to receive, the fact that the phase noise is down 100 dB is not going to help you as much as you had hoped, right? So it's all how the amount of relative phase noise is very important, especially with respect to how big the jamming signal is relative to the signal that you're trying to receive. Okay? Now another reason phase noise is important is in digital communications, it results in basically an error vector magnitude degradation. And in OFDM systems, it results in inter-carrier interference. Now in this class we're not going to go into details of how digital communication systems work, but just intuitively imagine that you're transmitting some kind of PSK waveform where you'd like your symbols to line up like this on the constellation diagram. Well, due to phase noise, you're actually going to move around like so and reduce basically the area of these. Basically, you're going to fatten these symbols out due to this phase noise. Okay? It turns out that you can actually tolerate quite a bit of phase noise and not damage the digital communication system like PSK. Systems that use OFDM, or basically systems that take up a channel, split it up into subchannels, and use subcarriers, tend to be very sensitive to phase noise. All right. Okay, so those are some of the reasons why we don't like phase noise. Let's now review where phase noise comes from. And to to do that, we're going to present a very simple model of an oscillator that has noise in it. So this is LTI analysis, meaning we're going to assume that the oscillator is a linear time invariant system. And you might argue that's a really bad approximation, because an oscillator is, first of all, it's not linear, right? We kind of proved that linear systems can't oscillate, can't go into steady oscillation, and it's not time invariant. It's actually a periodic system, or nearly periodic. Nearly periodic because there's noise, so it's really quasi-periodic. So assuming that it's linear and time invariant is pretty gross approximation. Oh well, it's easy to analyze, so that's why we'll do it. Okay, so this is kind of a very simple oscillator. We have an LCR tank. We have a GM generator. Let me make this a GM generator. So the current I is GM times the input voltage, which has a noise voltage plus some voltage V1. Okay? This is a transformer that takes 1 over n of the output voltage V2 and feeds it back into the input. Okay? So what I've done is that so the difference between this model and what we analyzed in previous lectures is noise. I've introduced noise into my feedback system. Okay? And I'm just assuming that this transconductor can be represented with an equivalent input noise voltage. Alright, so this system is very easy to analyze. The voltage V2 is simply GM V1 plus Vn times the tank impedance, ZT. Or if I substitute what V1 is just V2 divided by n times ZT. And so that means I can write, if I group terms here, V2, 1 minus GM ZT over n is equal to GM ZT times Vn. Okay? And so that means I can solve for V2 as a function of Vin. Remember, before when we analyzed oscillators, there was no input, right? Now there is an input. This is noise voltage. Okay? So this equation tells me that this is the transfer function from Vin to V2, and I can write this in a slightly different form as GMR, but just divide numerator and denominator, multiply numerator and denominator by R over ZT. Okay? And R over ZT I can write as RYT, which is basically 1 over R plus J omega C plus 1 over J omega L. This is nothing but a parallel tank, all times R. Or I can write this as 1 over R plus JB times R, which is 1 plus JBR. Okay? So substituting for this and here, I have that V2 is Vn GMR 1 minus GMR over n plus JBR. Okay? And so let me now substitute for B. B is just this term here. And in particular, I'm interested in how this reactance changes for offset frequency very close to the resonance frequency. So B is simply 1 over J omega naught plus delta omega L plus J omega naught plus delta omega C. So omega naught, of course, is 1 over square root LC, and delta omega is much less than omega naught. It's a small offset frequency. Now if I substitute from this above equation, I have j omega naught c plus j delta omega c. And if I assume this offset is very small, I can write this as 1 over j omega naught L 1 plus delta omega over omega naught. And now I'm going to approximate that as j omega naught c plus j delta omega c plus 1 over j omega naught L 1 minus delta omega over omega naught. And so you can see that because we're omega naught is the resonant frequency, this term cancels out with this first term, and we're left with j delta omega naught c minus delta omega j omega naught squared L. Okay. But notice that omega naught squared L is 1 over c, and this j can be taken to the numerator, and it becomes a plus j. And so this whole term becomes 2j delta omega naught c. Okay? So this tells me that for frequency offsets close to resonance, the net reactance is quite small. It's just offset frequency times 2 times c. That's the amount of reactance that I get. Okay? Questions? Yes, David?
So from homework, we know that the oscillator frequency can be different from the ALC tech frequency if there's delay on the amplifier and so on. So that makes sense worse.
Yeah, so this is, you can always redo this analysis by taking that into consideration. Let's keep it as simple as possible for now. So in this system, there's no delay. Yeah, it can be worse, yeah. It will be worse, yeah, you're right. Okay, and let me also observe that, let me now just substitute this result here into this equation and observe that GMR over N is the loop gain, right? That's what we've been calling the loop gain. This is the loop gain at resonance for this circuit. So if I substitute that, I get V2 is Vn GMR 1 minus the loop gain plus JBR, and I just found that B is basically 2 delta omega C. So this really should be JB. Quick correction there. All right, so I can also write this, if you like, as N times the loop gain. And so now I have a function which doesn't depend on circuit parameters so much, but just depends on the offset voltage, the loop gain, and the N factor that I choose. Okay? Now, this is just the voltage at the output. Because this is a noise term, we can't really say anything about the instantaneous voltage. What we know is that the RMS value is basically Vn squared times this term squared. So A squared, A loop squared, 1 minus A loop squared, plus 4 delta omega squared C squared. I think I dropped an R as well, times R squared. So this was JBR. Whoops, just an R here. Okay? Now, somebody asked earlier, what's a Lorentzian? Well, this is actually the form, almost in the form of a Lorentzian. If I divide through, so a Lorentzian has a form of like A squared plus X squared. Okay? So what's interesting now is that if this is the voltage squared, and it's at some offset frequency, I know that if I integrate this over all offset frequencies, I'll have the total power in my oscillator. So I have the RMS voltage squared divided by 2. If I integrate this over all offset frequencies, that's the power in the oscillator. Okay? So simply substituting here, Vn squared, let's say it's a white noise source, so it comes out of the integral, and we're left with this integration. Okay? Questions? Well, if you go into a table of integrals, or if you go into Mathematica or something like that, and look up what this integral is, you'll find that it actually closes. So the integral is just pi over a. Okay? And so if we apply that to this particular integral, we find that the power of our oscillator is Vn squared loop gain squared 1 minus loop gain squared. Again, I'm saving you guys a couple steps of algebra. Don't expect you guys to follow, but you'll believe me, this is what you get. Okay, and this cancels out with that. All right. And so let's write this in a slightly different form. Let's write this as Vn squared times n squared over r, pi over 2, 1 over rc, loop gain squared, 1 minus loop gain. Okay. So what we know about oscillators is that our previous understanding of oscillators was that loop gain goes to 1, right? And here we see that if the loop gain actually goes to 1, it predicts that there's infinite power in this oscillator, which is not an intuitive result. So what this simple LTI analysis is telling us is that actually the loop gain can be close to 1, but it's not quite 1. It's just a little bit less than 1. In other words, the system with noise, so the system, it looks like a positive feedback amplifier. Remember, when you have positive feedback, as long as the loop gain is less than 1, it's still an amplifier. Okay? And an extremely peaky amplifier. Okay? In fact, we can quantify now how small or how close to 1 loop gain is, because we can just say that this should be equal to some constant, which is the power in the oscillator, right? I can measure how much DC power I'm drawing from the supply. That's the power of the oscillator. So I just equate that. And so if I now solve, so if I know that loop gain is approximately equal to 1, just to simplify the analysis, so now I can say this term's roughly 1 and move this term to the left-hand side. So I have 1 minus the loop gain is approximately Vn squared n squared over divided by r divided by the power of the oscillator times pi over 2, 1 over rc. Okay? And let's call this pi over 2, 1 over rc delta f rc. The reason I do that is because 1 over rc, of course, looks like a 3 dB frequency point for a simple RC circuit. The pi over 2 term actually comes from noise analysis. I know from noise analysis that if I put a white noise source into an RC network, it looks like that white noise source is not shaped at all by the network, but it's simply multiplied by brick filter with passband pi over 2 times 1 over RC. So we identify this as some kind of noise bandwidth. And so what you see here is that this is a ratio of the noise power, which is Vn squared over r, times some noise bandwidth, divided by the power of the oscillator, right? And for most good circuits, we know the noise power is much, much smaller than the oscillator power. So this is a ratio of a small number over, let's say, a large number, the oscillator power. in other words, this right-hand side is very small. So right-hand side is very small. Let's call it epsilon. So we have 1 minus the loop gain is Vn squared over R times n squared divided by 1 over power oscillation times delta FRC. Let's call this all epsilon, some small number. In other words, the loop gain is 1 minus the epsilon, 1 minus epsilon. Okay? So the conclusion is that if I have noise in my system, LTI analysis, let's call this the LTI conclusion, is that loop gain is very close to 1 but not quite 1, and the noise is shaped by a very sharp filter. Okay? Why is the filter very sharp? Because of the positive feedback, right? The positive feedback compensates for the losses in the tank, and so the net result is that there's an extremely sharp filter filtering out this white noise. And that's why this potentially will explain why the noise drops off so quickly as we move away from the carrier. Okay? Now, again, this is very, very simple analysis. I don't want to bore you guys, but it's good to do something a little more complicated. Let's do a little slightly more complicated circuit. Let's say, a real LC tank that has loss in it, so that therefore it has some noise, 4kT 1 over R delta F. Let's just call this IR squared. Again, let's take a GM generator, just like before. Let's assume that it has some drain noise. Let's assume it's a transistor, drain noise or collector noise if you like. And to be more general, let's assume that there's some input noise. This might be due to base resistance or gate resistance. Let's assume there's an input noise current. This might be induced channel noise, for instance, and there's some input impedance, Zin. So let's analyze this circuit in the same way that we analyzed our simpler circuit. What you'll find, again, I'm going to save you guys some time and you can do this at home, is that this system can be reduced to a simpler system that just has one noise source. Let's call this In squared. And this is V1. This is GM-V1. This is LCR. This is R prime in parallel with N squared Zin. So I'm going to take the input impedance of my transistor and refer it to the tank. Okay? And if I do that, I find the equivalent current is the sum of IN1. IN1, of course, just flows into the output. IN2, if I transform IN2 across the transformer, it gets divided by N squared. The input referred noise gets transferred to the output like GM minus 1 over NZN squared plus basically IR, which also just drives into the output. Okay. So once I've done that, I've simplified the circuit considerably, and I can rapidly analyze it. Okay. So the analysis is very similar to before. I just write that V out is GM-V1 plus IN, all multiplied by the tank impedance. I observe that V1 is minus V out over N. Minus because now I need to invert the signal because of transistors inverting the signals to get positive feedback. So if I substitute, I get GMZT over N, V out for that first term, minus INZT for that second term. And so I can group these terms and write, again, a transfer function all in terms of IN, and it looks a lot like what we saw before. Okay? And again, I'm going to just expand. I actually don't even need to do this. Well, let me just do it real quick. So this is the tank impedance. Let me define the tank Q as the effective R over omega naught L, or if you like, omega naught RC. So this is the loaded tank quality factor. And again, I'm interested in frequencies close to resonance, so I can write ZT as R over 1 plus JQ omega over omega naught minus omega naught over omega. And if we again let omega be omega naught plus some small offset, where delta omega is much less than omega naught, same approximation, this difference here is just 2 times delta omega over omega naught. Okay. All right, so now haven't done anything fancy. All I've done is really the same thing that I did before. And now I go ahead and substitute what the tank impedance looks like at some offset frequency, and it's going to be R plus 1 plus J 2 times Q, it's this term, delta omega over omega naught. This is the same thing we found before. I just wrote it differently instead of writing it as Q. Okay? So when I substitute for output, I get R over 1 minus the loop gain plus 2JQ delta omega over omega naught. Okay, so this is the same equation as before. Questions? Going a little bit fast, just so I don't bore you guys. All right, so crystal clear. Good. So the output squared, just like before, is IN squared, R squared, 1 minus the loop gain squared, plus 4Q squared, delta omega squared over omega naught squared. And again, this is that Lorentzian. Now for offset interest, for offset frequencies of interest, because the loop gain is going to be very close to 1, you can imagine that this term will completely dominate. So if I look at V out squared divided by the amplitude of oscillation, if I normalize it, that's approximately IN squared R squared divided by V out squared. That's that term here. This term dominates, so this term becomes omega naught over delta omega squared, and this term becomes 1 over 2Q squared. Okay. Where did I drop a factor of? No, that should be 4. Okay. So this is telling me that if I look at the amplitude of noise, if I look at the spectrum relative to the peak spectrum, it has a really nice simple form. It has a noise over signal, where IN squared R squared is effectively the noise power divided by the signal power. It has this form, which is the normalized offset frequency. So this is the normalized offset frequency. And this is basically the loaded Q of the tank. Okay. Which tells me that if I'm looking at this, again, on that log-log plot, this simple model is showing me a couple of things. It's telling me that this rate goes like 1 over offset frequency squared. Okay, that's right there. It also tells me that if I can lower the noise power in the circuit, this thing will move up and down appropriately. But usually you don't have too much control over that. It's pretty hard. What you do have control over, hopefully, is the quality factor of your tank. the better you can make the quality factor, the better the phase noise. So we see a 1 over q squared improvement over the quality factor. So what we really want to do is use the highest q possible to lower the noise. Okay? So this kind of simple analysis more or less tells us two things, or three things if you like. It tells us that, you know, the offset, the phase noise is going to drop like 20 dB per decade. Okay? It's going to depend on q squared. So if you can improve your q by a factor of 2, the phase noise will improve by a factor of 4. And it depends on the noise power, effective noise power at the output of our amplifier driving the tank. So if I can somehow lower that power, it's going to help things out. It also tells me that if I can increase the magnitude of the amplitude of oscillation, it's also going to help. Because it's a relative, phase noise is a relative quantity. It really depends on the power of the noise normalized to the power of the signal. Okay? Questions? All right, so using the same analysis that we did before, we find that the loop gain is IN squared R squared V out squared pi F naught over 2Q. And what's really interesting is the minus 3 dB bandwidth of the Lorentzian. So if I go back to the spectrum, when this term is equal to this term, the power drops by 3 dB. So basically that means 1 minus GMR over N, that's the loop gain term, is equal to 2Q delta F, which is F minus F naught over F naught. Okay? So I'm equating this term with this term, or the square root of this term with the square root of that term. Okay. So now I'm going to solve for delta F. Delta F is F naught over 2Q, 1 minus the loop gain. And if I substitute, that's noise squared R squared over VO squared pi over 4Q squared times F naught from here. Okay. And now you can see, you can actually just take an example, a real transistor oscillator, and calculate what the 3 dB bandwidth is. So let's take an example. Let's say that the noise power is 10 to the minus 22 amps squared per hertz. Let's say the loaded tank Q is 300 ohms. That's pretty reasonable. It's possible. Let's say the oscillation amplitude is 1 volt. Again, that's pretty reasonable. Let's say the center frequency is a gigahertz. And let's say the quality factor of the tank is 10. These are all reasonable numbers. Anybody have a guess if I plug in these numbers what delta F is going to be? Just guess, you know. You could guess a kilohertz, right? You could guess a megahertz. You can guess a hertz. Anyone want to just take a guess?
Kilohertz?
Okay, we have one guess, kilohertz. Anybody think it's going to be lower or higher? Less? How much less? Okay. Do you want to just say a number? You're not being graded on this. It's actually quite amazing. If you plug it in, if I didn't make an algebra mistake, it's 0.07 hertz. Extremely small, right? So that tells you that you're not going to see that flattening out unless you get extremely close to the carrier. Okay? And there's no way you can do this measurement with a spectrum analyzer. It's very difficult to do. So typically when you see phase noise plots, they start at a kilohertz away or 100 hertz away from the carrier. And in that region, you still see it rolling. You don't see it flattening out. You have to get really close to the carrier to see it flatten out. Okay, so this is, again, with lots of qualifications, a very simplified analysis of phase noise. it leaves a lot to be desired, but for many, many years, it was more or less the only way to understand noise in oscillators. I should attribute this to Leeson, so maybe we can go back to the very first lecture and give him some credit. So maybe slide number 3 or so would be the right place to do it. Okay, how about right here? So here we'll call this the Leeson model. Leeson didn't quite derive it in the same way, but effectively this is the result of the Leeson model. The Leeson model tells you the phase noise drops like 1 over f squared, and it depends on q squared. Just kind of what we've observed here. Okay, and then what Leeson did was, as a good engineer, he introduced some fudge factors. He basically said, well, this simple model doesn't fit measurements, so let's introduce a couple of fudge factors and then make it fit. And so if you look at the Leeson model, it has an f factor, which lets you adjust the relative amount of phase noise. And then he has a 1 over f cubed term to take care of this Closson spectrum. All right. Now, so let's try to do a little bit better and come up with a slightly more sophisticated phase noise model. And this model is basically what you might call an LTV phase noise model. So it's still linear, but it's now time varying. And a couple of people who really popularized this model were Ali Hajimiri and his advisor Tom Lee at Stanford. Okay, so this was Hajimiri's PhD thesis. Now the LTV model treats the system as a linear system, and it's basically starts out with a simple observation. Let's take a simple circuit like this. It's an LC tank, and let's attach a current source into it. And let's say that this is kind of like your noise, okay? And what we're going to do is we're going to make, instead of making this a white noise or anything like that, we'll make it a deterministic waveform. In fact, we'll make it an impulse. So at some time tau, we introduce an impulse into the system. Now, on this, when you have an impulse like this, this current source basically will see an open circuit through this inductor on this small time scale and see a short circuit through this capacitor. So all of the current will flow onto this capacitor plate, no matter when I inject this impulse. And so what we see, what the action of the impulse is to dump charge onto this capacitor plate, or possibly remove charge if the impulse is negative. Okay? So how does that play out if you have a sinusoidal oscillation going on? So there's two cases that Hajimiri points out. He says, let's say you have your oscillation, it's going on nice and steady, and then let's say time tau, this is time tau, at this point you introduce your delta function. Well, what happens is it's going to introduce basically, let's say it's in such a direction as to introduce negative charge. So let me turn it around, make the plot easier to draw. Okay, so that means that it's going to increase the amplitude of oscillation at that moment, but ever after that, oscillations will ensue just as if nothing had happened, just at a larger amplitude. So what we've done is we've dumped more energy into the tank, so the amplitude of oscillation's gone up. But if we look at the zero crossings of this oscillator, the zero crossings don't change. So case 1 is when the injection occurs at peak of waveform. Okay, that's very important, the timing of when we inject this peak. And the observation is the oscillation amplitude changes, but that the phase is the same. Right? It's crossing 0 at exactly the same time as it was before. All right? So any questions about this thought experiment? I find it actually quite amazing that Hajimiri came up with this theory based on this simple thought experiment. He just sat down with a simple circuit and played with it, and based on that came up with his theory. Still had to verify it, but that's how it all was born. Okay, the other interesting point to look at is when injection occurs at waveform 0 crossing. Okay, so let's draw our oscillation again. It's going along happy as can be. No one's disturbing it. But then at time tau right here, we're going to inject this nasty charge. This is time tau, and we want to find out what happens. So this dotted waveform shows us what would have happened if we hadn't disturbed it. But because we've disturbed it, we've actually injected charge at time tau, so we've changed its amplitude here, and now the waveform does something like this. And the important observation is that we've changed the phase. Okay? So apparently, at some times, our oscillator is not sensitive at all to injection of noise. Other times, it's very sensitive. Okay? Questions? Yes?
On the previous page, so the amplitude goes up, but we know on real oscillators there's also gain, amplitude regulation kind of thing, where it brings back. How does that mechanism affect phase noise?
That's actually a very good question. So here we're ignoring that. Any real oscillator would have an amplitude restoring mechanism, and the assumption is that the time scale of the amplitude restoring mechanism is quite slow, and it doesn't disturb this fundamental picture. In reality, you can get AM to PM kind of conversion, which would cause a phase shift. As the amplitude shifts, the nonlinear capacitors shift the frequency a little bit, and you end up with a net error. Okay? Here we're assuming that this noise is the total amount of charge, and even though I'm hitting this thing with an impulse, the total amount of charge is small. So this voltage shift here might only be microvolts. So the actual AM to PM is not going to be important. Okay? So this is where the linearity assumption comes from, is the disturbance, even though it comes suddenly in time, in amplitude, it's actually quite modest. All right? All right, so what we do now is we define a system that goes from noise current into, let's say, output phase. So it quantifies how much noise can change the phase of a system. And we define, because we're assuming it's a linear system, we define an impulse response function. And because it's time varying, it has two arguments. The assumption we make here is that the impulse response function, 1, takes on this form. And let me argue why this form makes sense. So this is just a unit step function. Okay? It tells me that the system doesn't respond to this noise until the noise happens, and when it happens, it responds instantaneously, okay? Because it's an impulse. This function here is just some periodic function. Okay? And for now, let's just say this is a normalization constant. This is actually the charge stored on your capacitor, the maximum charge stored on the capacitor. Okay, now why is this form valid? Well, in particular, I haven't really said anything. All I've said is it's a linear system and it's linear periodic. That's mostly the most important thing, is that its response is a periodic function. And the reason I think it's periodic is because I'm assuming my system is periodic and its sensitivity to noise varies over its cycle, but it's periodic. So this is the most important assumption. After I've written down this function, actually, more or less all the results fall through. So let's talk a little bit more. Let me again remind you what this function is. This function says that you have the system I've defined is kind of funny. It starts with a noise current, something physical, but it ends up with some output phase. It's the error in the output phase, right? And so this is very easy to determine experimentally in a simulator, let's say, but very hard to actually measure in practice. So the idea is, the way you would measure this in practice is you would introduce delta functions of current, little spikes of current, at different times in this period. And you would look at the resulting output phase. And you would plot the output phase error as basically a function of when this occurred. And you'd end up with the impulse sensitivity function. So it might look something like, oh, I didn't define this. So Hajimiri calls this gamma function is called the impulse sensitivity function. All right. And if I were to take an example, let's say I have an oscillator that's oscillating something like this as a function of time. If I inject charge at each point in its period and plot the resulting phase error, I'll come out with something like this. I'm going to plot gamma omega t versus t. And what I find is that when this thing apparently does these zero crossings, this oscillator, it's very sensitive. And so the impulse sensitivity function might look something like this. So this ISF is telling me that my system is not sensitive at all to noise at this point, but it's very sensitive at these points. Okay? All right, questions? Yes?
So why did you assume it's linear response?
The way that it's justified is what you can do is you can inject very small charges, observe the output phase, and then keep increasing the magnitude of total charge that you dump on that capacitor and observe the output phase. And you find experimentally that it's very linear up to a very large range. Okay, so it's an experimental observation, really. All right, so if we know the impulse response function, it's a linear system, so we can calculate the actual response for any kind of deterministic input like this, right? And if I just substitute here, okay, so if I substitute for what ISF for the impulse function, this is the integral I have. Now the important observation is that gamma of omega t is periodic, so I can write it as a Fourier series. Cosine n omega naught t plus some phase, n is equal to 1 to infinity. So if I substitute this in now, I have that the output phase looks like 1 over q max c naught over 2 times the integral of I of t plus sum n equals 1 to infinity cn integral minus infinity to t I of tau cosine n omega naught tau d tau. So phi of t is the phase function due to a deterministic signal I of t. Okay. And the transfer, so one way to interpret this equation is I have some disturbance, and I'm going to normalize it by Qmax. This gets multiplied by gamma omega naught t, this periodic function. I integrate this function up to time t. This gives me a phase error, and the actual oscillator output then is cosine omega naught t plus phi of t. In other words, this phase error modulates the phase of my carrier. All right. Now, it's interesting to observe this phase modulation process. So, let's start out with a sinusoidal noise current. Remember, this analysis is valid for any kind of signal source, not just noise source. In fact, it's more valid for deterministic sources. So what I'm going to introduce is a noise current at some frequency m omega naught plus delta omega. So I'm going to introduce a little sinusoid at basically a small offset away from one of the harmonic frequencies. So I of t is going to be Im cosine m omega naught plus delta omega t. All right. So now all I have to do is substitute this term into here and perform the integration. Before you do any math, you should observe that basically it's to a very good approximation. All the terms that involve orthogonal functions are going to basically integrate to 0. So if I take cosine of m omega naught plus delta omega, let me just expand this. I can expand this into cosine omega naught, so I could write this as I am cosine m omega naught t cosine delta omega naught t minus sine m omega naught t sine delta omega t. So if I substitute this equation into here, you can see in particular that when I multiply here by cosine, if n and m are different, then this integration is essentially going to go to 0, right? So I'm integrating over several cycles. So the only term that will survive is when n is equal to m. Because when n is equal to m, this first multiplication produces a cosine squared term. Second term produces a sine times cosine term. Sine times cosine, again, they're orthogonal. I integrate them away. So at the end of the day, at the end of the slaughter, the only term that survives is this term with m equals to n. And so if I take this phi of t and integrate it, the only term that I need to integrate, I get cosine squared here, so I get 1 plus cosine 2 omega naught mt divided by 2. Again, cosine 2 omega naught t integrates to 0, so the only term is the constant times cosine omega t. Integrate cosine omega t, I get sine omega t. All right, and you can also do that at home if that was too fast. So the important result is that I inject a tone at some offset frequency close to basically one of the harmonics, not necessarily the oscillation frequency. And from the phase perspective, I get two tones centered about DC, and one is positive and one is negative, and the tone basically, its magnitude goes like 1 over delta omega. So the closer I inject that tone into my system, the more the phase deviates. Okay? And this whole thing gets multiplied by Cm, where Cm is the mth coefficient of the Fourier expansion of the ISF. So graphically, that means that if you have a general now waveform In squared, let's say it has some kind of spectrum like this, where this is the 1 over f noise. Say this is omega naught, this is 2 omega naught, this is 3 omega naught. Then what we find is that any noise including the 0th harmonic, which is DC, will get transferred into the power spectral density of the phase. So the power spectral density of the phase at some offset delta omega has a contribution from tones around the harmonic at a frequency delta omega, at tones around the second harmonic, the third harmonic, and so on, and most importantly the DC as well. So this gets converted to here through the C0 term. This gets converted to here through the C1 term. These guys get converted here through the C2 term. These guys get converted through the C3 term, and so on. And the resulting, so this is the phase. If I now look at the output voltage, the resulting spectrum turns into a Lorentzian. And for carrier frequencies away from the center, mostly all of this noise directly translates to here. And in fact, let me give you guys a quick interpretation of why this flattens out. The reason this flattens out is because no matter how much phase deviation you have, the cosine function is always bounded. So that's why the actual voltage waveform flattens out like this. Okay, unfortunately I have to stop here. We're going to do the evaluations at this point. Is the TA also evaluated today, or is that separately? Okay, all right. So evaluations are very important. I encourage you guys to take your time and evaluate myself and Al Molnar. And if you basically have comments, I really appreciate them. You know, those get read very carefully.